definitions and then why I was interested in this problem to begin with. Okay. So first, given two relational structures, in the same signature L, I'm going to take this classic notation B choose A. I should give them these names, A and B. Is going to denote the subsets of B, or the substructures of B that are isomorphic, induced substructures, isomorphic to A. And I think most people here are very familiar with this, but I guess as a point, this is somewhat different from, say, subgraph, whereas if I have this graph here, I'm not looking at subgraphs when I take these two. I can't look at this as a subgraph like one often would, or maybe with colors. One might often think this is a subgraph like this, but we have to have things induced, so this is not okay. Right. That's the proper substructure induced by those by that set. And so now that you have notion of structure, you can discuss some basic Ramsey theoretic results or structural or Ramsey theoretic statements. So given a class K of L structures, the Ramsey degree, or the small Ramsey degree of A, this is relative to the class it's in, K, is the smallest. We'll give this a name as well, TA. Is the smallest T such that for any medium-sized structure in the class, for any list set of colors you give me, or a number of colors you give me, there is some large structure C such that for every coloring, a lot of quantifiers, decay many colors. Oh, sorry. You can find some medium-sized copy inside B or inside C, such that you meet at most T many color classes on this copy B. Right. So classic example that most people are familiar with is, for example, in the case that K is the class of linear orders or finite linear orders. Then the Ramsey degrees are precisely 1. So the class is Ramsey. Okay. But of course, it's not always the case that the Ramsey degree is equal to 1, right? So there are some classes for which this is not true. For example, posets, this is not the case. Metric spaces and graphs, this is not the case. But what's interesting is despite the fact that they're not Ramsey or have Ramsey degree 1, they have a Ramsey degree and it can be computed. So the main method that one uses to actually compute the Ramsey degree is relational expansions. So I guess briefly, or just a the TA is usually computed and I'm gonna put this in quotes for a sec. This is a bit more than this usually. Right. So some two examples of where this was done was I think this initially one of the first instances is 1997 by Fouché, where he looks at linear extensions of finite cosets. And if you look at this relational extension, and then you make an application of the Graham-Rothschild theorem, you get that you can compute the Ramsey degrees. So the idea is in the linear extension class, it is Ramsey. So you can compute this explicitly, and then from that, by counting the number of expansions, you compute this, right? Another example. You also have metric spaces by adding linear orders and using a part-byte construction. Okay. So this is really nice theorem. Well, okay, well, there's a couple. So one that I think everyone may be familiar with is, there's the KPT correspondence. Which is given K relational of finite structures for say with for say limit K, you have these two conditions where you have a comparison between dynamics and rigidity or combinatorial rigidity. So K is Ramsey and consists of rigid elements. And then you have the automorphism group of the per se limit is extremely amenable. And then it's interesting where the dynamics comes into play with relation to expansions is I'll skip some of the literature. There's a lot done, but the main result in from 2014 to 2018, what I'm interested in is these two theorems, or a theorem, two theorems, and then I guess a question. So essentially, in 2014, you have that by Zucker that you can actually compute the idea of using relational expansions is essentially the only way you can do this. So let me get the exact theorem. Okay. Go off of memory, sorry. Given a for say class K, with for say limit K, following are equivalent. So you have finite big Ramsey degrees. You have a dynamical statement. So the universal minimal flow, which I won't get into too much detail of what this is. The automorphism group is metrizable. And then I guess the the reason why I'm interested in relational expansions and why I want to look at relational expansions of larger structures is you have there exists a relational expansion. So you get some expansion of K such that you can compute the Ramsey degrees explicitly as expansions. Right?
Slightly different definition of listing. One usually takes embedding rather than and for listing to old.
We need rigidity, right? Or would we need?
Well, there is no rigidity.
Yeah. Okay. We'd have to have that, right? Correct.
I don't know. I think Andy's theorem is about
Embedding Ramsey. Okay.
and the quality and divide by the sample is more than something like that.
Yeah. So it's sort of like okay. Yeah. So it's sort of like divided by number of automorphisms, right? Yeah.
Well,
This. Something like this.
slightly different.
Yeah, he uses, okay, thank you. Yes, thank you. Okay. So,
Is that the number of expansions of A and K star? or-
yes, that as well, thank you. Right, so for example, the order property is when you can compute explicitly by adding a linear order, and you get what's nice is you also get an explicit computation of the universal minimal flow as considering the logic action on the relation and then take its closure, the relation that you're adding. So this is actually technically what you do in general as well. So for other structures. So if you even look at Big Ramsey, this is kind of the same strategy that's still done for the most part. So I guess brief reminder, given a structure finite, a finite substructure of okay, the Big Ramsey degree of A in K, I'll denote T AK, is the smallest T such that, and then definition looks similar to before, but actually quite nicer. So for every number of colors you give me, for every coloring you give me of the large structure K, I can find some copy of K inside itself such that, again, you meet at most T many colors. With the canonical example being, again, take K to be omega. Right, and in which case the Big Ramsey degree is 1 for all finite linear orders, right? So if you want to, so the way in which you compute these, if you look at, say, how Laver does this for the rationals, and then Devlin gives the exact computation, is it's still technically, although not exactly, the type of relational expansion. So this is the brief history on how that's done. So for the rationals, the idea is that this is ostensibly infinite binary tree. And then you can take a natural linear order on it. Now this infinite binary tree itself has a structure associated to it, right? So then when you're computing big Ramsey degree, you're applying a Ramsey theorem here to say something about Q, right? And so let's say Q and Q. All right. Slaver, I believe this is 71. And then the exact computation is by Devlin. His famous odd tangents.
You said that one?
Oh, I'm sorry. Yes, Devlin. Sorry. Right. So the idea is essentially the same as you're taking some structure where you have a Ramsey theorem, particularly Millikan's theorem, and then you'll look at expansions. So maybe I just briefly, because this will come up later. The Devlin types, as they're called, are essentially anti-chains with this property that their meet closure is a tree of size 2n minus 1, and each node appears on a unique level. So for example, if you want to go back to the classical, you also have this, they go to the left thing, but technically, these are the two for in the case that n equals 2. And this coincides with Sierpinski's coloring, essentially, is the rational orders is essentially going left to right on the tree, and then the Sierpinski coloring is asking, given it to your natural well ordering, which is given by height, how does the height order correspond with the rational order? And so that's how you get to. So you're counting expansions of pairs. Those are the two expansions, essentially. Okay. So then you have again this theorem by Andy. Or let's say definition first, and then the theorem. So you say K admits a big Ramsey structure if there exists an expansion K star of K such that, okay, well, for one, this is precisely an expansion, right? So two, you have that the big Ramsey degree of A and K is precisely the number of expansions of A in K star. And then the above is witnessed precisely by that coloring. So essentially the essential or persistent patterns are precisely those patterns you get from relational expansion, right? So then natural question to ask is whether or not big Ramsey degree is equivalent to the emission of a big Ramsey structure. So that's what I'm interested in. It's still open. And my goal for trying to analyze this problem was to look at relational expansions more generally And I came up with some interesting secondary stuff about product Ramsey theorems as well. So I should note there's a dynamical characterization as well, which also makes this nice, right? But I'm not going to go into any dynamics. The idea being is that having a big Ramsey structure tells you something nice about dynamical properties of embeddings of K into itself, that semigroup, when K is for say. So there's a question. So we know big Ramsey structure implies finite big Ramsey degree, but does a big Ramsey degree, finite big Ramsey degree, imply there exists a big Ramsey structure? So is there a nice way to add relations on? So if I could draw a little diagram of what I'm going to discuss is we have big Ramsey structure implies finite big Ramsey degree. And what I thought was a related statement to finite big Ramsey degree, but a much stronger statement is finite list of canonical partitions. So I'll get into what I mean by that, but this is essentially a meta statement that forget reducing to coloring to some number of color classes. I want to reduce all possible colorings into some finite list of possible colorings you can take, right? This, of course, is stronger if you have a finite list. And a related question that came up is this problem of Masulovich, which I have a positive answer for, given some conditions here. So provided that the language you're working with is such that for every n, the set of relations of arity n is finite. So a quite natural condition. Then you have something I denote the box Ramsey degree, the natural projective analog for this. And what's nice is that this is actually equivalent to this. In fact, finally many relational expansions, period. Up to reduction. This up to reduction is a key point, which is what makes this thing still unknown. Are there any questions about the setup so far? Mhm.
In the integration that you say you provided a language and that property, is that property needed in both directions?
Yeah, so the idea is if you have okay, how do I in order to have a finite box Ramsey degree, you're going to need that anyway, essentially. The idea being is that if you have infinitely many distinct relations of some arity, then when I tell you what box Ramsey degree is, those relations tell you precisely how to color n tuples of singletons. Because if the relations are separated, they in themselves give you infinitely many distinct color classes. So nothing's really interesting outside of that case. Okay. Okay.
fixed finite languages, right?
Yes, yes.
So
yes.
it doesn't seem like.
No, it's not too bad. Essentially, it's that up to, you know, right, when you're only cutting a segment and looking at n copies and stuff like that. Okay. I want to go from here. I guess let's start with what I mean by box Ramsey, and then I'll walk into the other stuff. So the box Ramsey statement is essentially a product Ramsey, a product big Ramsey statement. I should also note, while I'll try to make it very clear when I take K to be countable or anything like that. A lot of the stuff actually won't really require that, or that it's for say or anything. Obviously, in some cases, you're not going to get big Ramsey degree if K is of some cardinality, but it's not relevant to some of these statements. They still, a lot of these things still hold. So given a tuple of substructures, so A1 through AD, finite substructures. Okay. The box Ramsey degree of the tuple, I'm going to denote this. Okay. Looks quite similar again. Is the smallest t such that whenever you give me some number of colors, and now some coloring of the product. Here's why I call this box. There exists K prime, only one that I need. Such that the number of color classes, when I look at K prime and all the tuples inside it, this is less than or equal to T. So the reason why I thought of naming it box Ramsey is because precisely I'm thinking of boxes when I was thinking with respect to the rationals. So this is your copy K, and then this is your copy K. The idea that I only want this one existential here, which will be relevant for when I talk about relational expansions anyway. This is really what you want. You don't want to start changing things up. You can, but it's not as valuable. The idea is I find some most too many copies inside a box. Okay. I guess any questions so far? I guess maybe let's give like a quick example of so one of Dragon's guesses for a product Ramsey theorem or a product big Ramsey theorem, because it holds in the finite setting. You have a product Ramsey theorem, and it's precisely what you think. The Ramsey degree of the product is the product of Ramsey degrees. So that's a natural guess, and it's just not the case. So I won't do the exact equality. We'll do that after, but say if you look at two singletons, or maybe I'll write them like this. If you look at the two singletons inside omega, it's at least 3. It's actually precisely 3. The naturals, if you want a well order, countable. No, that's fine. Yeah. That would be the most interesting case, but you can get all this for non for say. Yeah, and the same thing with the relational expansion, which is nice as well. Finally, many relational expansion. So the coloring in question is, when I'm coloring singletons, you might as well just color a pair of omega, right? with three many colors. And a natural one to think, and is essentially is the only one, is you color in accordance to how A and B relate. So of course, by this existential here, no matter which copy of omega you get, you're going to meet all three classes. So the idea is that's actually the counting these is precisely how you compute you'd compute a box Ramsey degree, is looking at all these sort of tracial classes. So explain what I mean. So if you give me two tuples, this idea, by the way, stems from two places that I'm going to write right now. This stems from work of Laflamme, Sauer, and Vuksanovich, in particular Vuksanovich and his thesis. And that itself is motivated by the classic Erdo-Schredo canonical partition result. So here's the idea, is if you give me two tuples, I'm going to say they're equivalent. If and only if there exists isomorphism to their unions. With a property that respects the order. So fairly natural thing to look at. And this itself is a equivalence relation. And so if you're interested in a box Ramsey degree or product Ramsey degree, this is the natural equivalence relation you probably are going to want to take a look at, because if you notice, I guess a small thing to notice is whenever you give me a copy of K and K, when I restrict to its tuples, it's going to still meet every one of those classes. Right. So that equivalence relation essentially gives you a lower bound for what a box Ramsey degree ought to be. And using that equivalence, you can compute this precisely. And P C class P intersect this product. That is not empty. Right. Simply take K primes copies in that organization. It'll be there. Since it's a isomorphic copy of the category. Any questions about that observation? Clear? So then the idea is if I want to prove this, if I want to compute this box Ramsey theorem, and we have this natural lower bound, then what I want to do is look at those classes individually and talk about colorings on those classes. I guess also briefly to relate to that question previously asked on infinitely many relations of summarity, note that this is precisely where you would get an issue for finite box Ramsey degree for all tuples, because you take if you have infinitely many relations of cardinality, say 5, look at 5 singletons, right? And then you have infinitely many classes there. That'll tell you a really bad coloring. There's no hope getting finally many color classes. Right. Okay. So what I'm gonna do. Oh, sorry. Now we have these tracial classes. So let's compute. Let's work with them. So. Okay. Start with the definition quickly and just make life easy. So, given a tuple, this is the way I like to think of this is let the trace of x1 through xd just be the union. I'm thinking sort of like linear algebra trying to reduce things to a one-dimensional setting. It's nice notationally to have this. Then instead of writing union every time, I think it's clean. It's cleaner. What I'm trying to express here, collapsing down like projectively what copy of or what structure I'm getting here. So, but lemma given class P. And suppose with trace P, so that's the isomorphism type when you take a trace of anything here. The trace map goes into copies of B, but it's not 1-to-1, but it's ought to 1. So projecting down gives you an automorphism of B-to-1 map. So why is this true? Well, I guess quick proof. Given these two things are isomorphic, or given these two things are in the same class, right, then there exists essentially an automorphism, right? The morphism between the two is essentially you're encoding some type of automorphism from B to itself, right? Right. So in particular, when the traces are the exact same, it is an automorphism, right? And then the other direction is similar. They're the same in the same class, then there's some automorphism that witnesses that. So it's an automorphism to one map. Any questions about that? Or keep this up? Yes, keep this. Yeah. Okay. So then if it's an automorphism to one map, then naturally, if I want to prove a Ramsey property for P, it suffices to actually work here, and the trace will do the rest for me, essentially. So here's the idea. It's everything from here is really classic tricks in the field, nothing too crazy. Call this a proposition, I guess. Given a tracial class P and a coloring from the tracial class into K many colors, there exists a copy K prime and K such that chi only takes on, finish writing this. A big Ramsey degree of B and K times the number of automorphisms of B. And this is the best you can do. As a corollary, so once you prove this corollary is the box Ramsey degree of a tuple is precisely a sum over the tracial classes the big Ramsey degree of that class of the trace the representative of that class times the number of automorphisms it has. Right. So then again, you need these finite and these finite in order to get that phenomenon. Okay. I guess the proof of the proposition. It's a fairly classic argument. So start with the coloring. P and K. And now consider a new coloring. All right, I want to transfer the question to in a place I actually know I have Ramsey degrees. Consider chi hat. Two to the K. So subsets of set of size K given by the color I'm going to give to some B prime is going to be the set of colors of some tuple where the tuple has trace equal to B prime. Right. I guess something to note is by our observation. That's precisely. It's a set of size automorphisms of B. So assuming B has finite big Ramsey degree, we have some coloring of, or I guess, are there any questions about the coloring first? I think the idea from here is clear though, right? Okay. Given you have this new coloring, chi hat, you can find some K prime. Such that this thing meets at most the big Ramsey degree of B many colors. Right. Note for any tuple, in your product, where now you take K prime, Are you staying inside this tracial class? The color of the tuple is in here. Right? The definition. So there are most T of these I need to worry about. And consequently, there are most odd B times the big Ramsey degree I need to worry about for these. Oh, sorry. Okay. Any questions about that? What's more interesting is the consequences of this personally. It's nice that there's a productive notion of big Ramsey degree. But what's nicer is the immediate results you get as using it. Mhm.
So this is finite big Ramsey degree implies finite box Ramsey degree.
Mhm,
In the other direction, it's obvious. It's just like a one-dimensional.
Yeah, thank you. Yeah. Okay, so here's a crawler. Suppose, or maybe let's start with a definition, or okay. How do I want to do this? Okay, let's do a definition first. Okay. Given some collection of tuples, we say it has Ramsey basis, say Ramsey basis or basis of relations if there exists some finite set of relations such that for any relation R on the product, there exists R hat in B and K prime and K, copy of K and K, such that the relation R hat is the same with respect to K prime. Okay. So this comes immediately from, or this can be computed, this list can be computed using this box Ramsey degree. If how do I want to do this?
Yeah, there's a bold B up there that should be a curve.
Thank you. Sorry. Yeah. Let's just do it with one structure. It's clear to see how to do for multiple. Hopefully it's clear to see for multiple. The singular structure too. This is the most interesting when it comes to equivalence relations as well. Exists on a Ramsey basis. Of binary relations. Copies of A. I say binary, what I mean is you're taking pairs here, right? I guess be a bit clear. But this also becomes interesting when A is a singleton because you're talking precisely binary relations on your structure or n array, d array, same thing. So why is this true? This is just a classic trick involving quote unquote bad colorings or persistent colorings or whatever name you want for the colorings that compute explicitly with the box Ramsey degree is. Proof. Take R on binary, i.e. it's a subset of the product, right? And consider essentially its indicator. So this is right. Let this be the bad coloring. I guess A, but we have one we know of already, A, bad coloring. So with the natural trick in the field is you consider now the product coloring. So consider colorings of pairs now. Consider my delta pairs of A. So be extra precise. So this is a T plus 2T coloring, right? But since we know we have finite box Ramsey degree here, we know we can find a copy of K prime where it's essentially a T coloring. And then you use a comparison argument using that chi was bad. So exists. Prime. Choose K. What's that? Meets T many classes. So the picture is stable likes to draw for this argument. Right. We know we're meeting at most T of many of these classes. But we know that every class here has to be met exactly once. right? This guy was a bad coloring. I can't dodge that these color classes. So consequently, on K prime, I have some selection like this, right? So there exists some color class such that A prime are a double prime if and only if how do I want to say this? So then as a consequence, you have thus all relations built from Chi's color classes form a basis. You consider all possible relations that you can build from these color classes. And there are 2 to the T many. This gives you an exact list of all of them, or all that you need. So I guess as a small segue, let's go back briefly to omega. You have all the relations there. So they're essentially, since the structures are rigid, there's no automorphism thing to worry about. Since big Ramsey degrees are 1, there's nothing there to worry about. All you really need to worry about is tracial class. Those compute all of them, right? So in case of omega, let's say I have d many of these. Equal the number of sim classes. So in particular, this gives you that statement I mentioned earlier. This is precisely 3 because those are the classes from that coloring, right? And as a consequence, you get Ramsey's theorem back from the 30s. That the only relations you need to consider expanding omega by are less than or equal to, or equality, constant, and complements. Complements. Of course, there are 2 to the 3 many, which is 8, right? And you can do them in general. For any d, you get the number is, or just, I'll just compute this, or state what it is. For any d, this is precisely the sum of all surjections from D to a K-size set. So you have a full computation of all the ones you need for omega. An interesting class of relations worth considering is equivalence relations, right? They're the ones that I initially wanted to look at to begin with. And so from this note, you get, with a bit more work, you get Erdos-Rado's theorem. You get that there's a finite list of equivalence relations, but you need to run through the relations themselves to see that they're precisely the projections. So some work has to be done there. But another corollary is Erdos-Rado's partition. Um, so what I want to do from here is I wanted to conclude Fuksanovich's initial work and give an exact list of what the equivalence relations would be on the rationals. I don't have the exact list yet. I'm getting quite close to it. But I did find a nice application in the case that your structure has some fairly strong homogeneity conditions. Fairly strong. So let me say this. I won't go too much into the details of these statements because they're quite complicated. But given A is for say, that's not that complicated. A has AP plus, more complicated. L finite, fairly restrictive. And something I'm gonna draw. Picture. And this, so what I need, this homogeneity condition I'm gonna need is if you give me a pair of points and you give me two types over this point, I don't think this statement is equivalent to STAP, which is why I need it. So if you give me one type tau over this point and another type, say delta, say, or tau 1 and tau 2 over this point, I can find a point, a singular point, which sees tau 1 with respect to the first and tau 2 with respect to the second. Okay. So something like you have this for, say, the rationals and random graph. The entire family of random graphs, actually, except for the Henson graphs. But given you have these two properties, there are only two equivalence relations you need on singletons. Right. The trick is using these SDAP plus classes. If you want to compute their Ramsey degree or big Ramsey degree, you have to look at a different version of Devlin types. So you're still looking at. So I'll show why this is true for the rationals, and this comes true generally. But I guess let's start with a proof. So take. Yeah, no, it's very challenging. Yeah, so this is okay. So maybe I'll state maybe I'll say the theorem then, a different theorem. So it's the substructure disjoint amalgamation property with some extra stuff. So this theorem of Coulson and Patel. Given K with SDAP plus and K say K is indivisible, and moreover you can compute big Ramsey degrees precisely by counting when you move to the coding tree, you count anti-chains essentially that encode or envelopes of A. It's very, very complicated. I definitely don't have time in like 20 minutes to go over all this. But I'll draw a picture for, say, the rationals, and then hopefully it can be you'll accept that this is what happens just generally.
The conclusion of the theorem that TA can be calculated in a certain way. You say K is divisible, and then you go down.
Yes. Teachers. Putting A encoding tree. Yeah. I'll just stick with why it's true for the rationals. And so for the rationals, you have your two Devlin types, right? Yes, with all these extra stuff. Yes. For the rationals, Devlin types for pairs I drew before. There's just two, right? Associated to the Sierpinski coloring. Right. So what are the classes associated to this box Ramsey degree for a pair of points? If I want to look at, say, an equivalence relation. You have the singleton, right? You have this Devlin type and you have this Devlin type, right? And so any relation is built from a collection of these classes. So if E is an equivalence relation, generated by these classes, then two cases. Case one is E only has this as a class. Right, so it says two things agree if and only if their tracial type is a singleton. Well, then E's just equality, right? Or E, let's say E is equality instead of having to write E equals, it's equals. Yeah. Here's the more hand wavy statement, but it involves transitivity. So suppose, and then without loss of generality, E has this type, right? So if E says these 2 points are related, note that, I'll do this over here. If he says these 2 points are related, then if you look at the entire tree, there's a trick. It's not too high. It's up here. Consider this arrangement. Say X, Y, and Z. So with respect to E, E says X and Y are related, but for the same reason, it says X and Z are related. They have the same passing type and whatnot, or Devlin type associated with these points. So since X and Y.
Could someone move the camera to point at the picture?
Huh?
Thank you.
Well, then you just apply transitivity and symmetry from here, right? But then, in other words, you have this type as well. Or maybe. So E must be generated by this type as well. So the similar general argument that works on the rationals gives you that there are two equivalence relations. So either you get back to the indivisibility, your coloring was finite, or if it wasn't a finite coloring and it couldn't be reduced to finite coloring, it could be reduced to equality. So an enumeration of a structure. So those are the only two colorings, provided these strong homogeneity conditions. Any questions about that? I think I have one last small thing I can show from here. One more big Ramsey application for computation. Try to be quick here. Suppose you have two classes of finite structures. This will be very, very fast. I and K denote this exponentiated class as the class of pairs. Where A is some index structure and L is some labeling into K. This class has a nice notion of embedding, similar to what Laver has for, I guess, indexed linear orders, right? So an embedding from is a map F from A into B and embeddings by GX, X and A from a label of X into the label at F of X. So for example, say linear orders and graphs. Right? This is a slight generalization of diversification classes studied by Kubish and Shala, where I, in their case, is essentially just powder, so points with no order. There's a natural, in a somewhat categorical setting, notion of a Fusset limit for this class when I and K are Fusset. So note, or I guess observation. And K Fusset implies this is Fusset. In the case when K equals I. The limit is well, picture. It's K, and then on each section, which is a label, it's just K again. So then from this image, I hope it's somewhat clear is in this category, you have big Ramsey degrees as well in the case that K equals I. But I still have absolutely no idea what happens when K is not equal to I. I have a guess, but there's no natural way to correlate these two things. Okay. That's all I have.